Bismillah ar-Rahman ar-Rahim. We now consider applications of eigenvalues and eigenvectors. Important applications are to difference equations and differential equations. So we will take up difference equations first. A very interesting example on difference equations is the Fibonacci numbers. This is a sequence of numbers in which each number is equal to the sum of the two previous numbers. Starting with f0 equals 0 and f1 equals 1, every new f is the sum of the two previous f's. So the sequence is 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, and so on. And this comes from fk plus 2 equal to fk plus fk plus 1. So the problem now is to find the Fibonacci number f100, for example. We can do it the slow way by continually applying the rule until we reach f100. Linear algebra gives us a better way. The key is to begin with a matrix equation, uk plus 1 equal to a uk. So according to the definition, fk plus 2 equal to fk plus 1, we will have fk plus 2 equal to fk plus 1 fk, and fk plus 1 equal to fk plus 1. So putting this into a matrix becomes uk plus 1 equal to 1, 1, 1, 0 times uk. Okay? And uk is fk plus 1 fk. So every step multiplies by a. After 100 steps, we reach u100, which is equal to a to the power 100 times u0. u0 is the starting vector, which is 1, 0. Okay, so u0 is 1, 0, u1 will be 1, 1, u2 is 2, 1, u3, 3, 2, u4, 5, 3, and so on. The Fibonacci numbers come from the powers of a, and we can compute a to the 100 without multiplying 100 matrices. This problem is just right for eigenvalues. So we form the eigenvalue equation, which is the determinant of a minus lambda I. So it is the determinant of 1 minus lambda, 1, 1 minus lambda, and it gives us the characteristic polynomial lambda squared minus lambda minus 1 equals 0, with solutions lambda 1, 1 plus root 5 over 2, which is nearly 1.618, and lambda 2 is 1 minus root 5 over 2, which is nearly minus 0.618. Okay, this number is the ratio of the most elegant rectangle, the most beautiful rectangle, which the Greeks discovered. The length to the width of the rectangle is 1.618. This is used by people, by architects, and they call it the golden mean or golden ratio, okay, or golden section. So now we calculate the eigenvectors by substituting for lambda 1, lambda 2, and for example here, if we eliminate above the second row to make the first row to zeros, we get x1 equal to lambda 1, 1, and from the second row, okay, it's obvious. For the second eigenvalue, it will be x2, lambda 2, 1. These are the two eigenvectors. Using the eigenvectors as a basis, we can write the initial vector u0, 1, 0 as a linear combination. Okay, so 1, 0 is c1 to lambda 1, 1 plus c2 lambda 2, 1, or the eigenvector matrix S times C equals u0, which is 1, 0. Okay, and since S is invertible, okay, so C is S inverse times u0, and the determinant of S is lambda 1 minus lambda 2. We divide by that, and then we find S inverse, okay, and U0 will be x1 minus x2 over lambda 1 minus lambda 2. Okay, so AU0 multiplies each eigenvector by its eigenvalue. Okay, so if we take a to the power 100, it will be lambda 1 to the 100 times x1 minus lambda 2 to the 100 times x2, all divided by lambda 1 minus lambda 2, which is determinant of S. So we want now F100, which is the second component of U100, okay, because U100 will be F101 and F100, so it is the second row. Okay, the second row from this is the second row of this equation. Okay, so it will be 1 over lambda 1 minus lambda 2 times lambda 1 to the power 100 minus lambda 2 to the power 100. Okay, now if you calculate lambda to the 100 from the eigenvalues, you will come up with a number approximately 3.54 times 10 to the 20. So F100 is the nearest integer to the first term, because the second term is a small number, less than 1. So when you raise it to the power 100, it becomes negligible. I think it is to the power 10 minus 21. So it is really very small, you can ignore it. So it is the nearest number to this one. In fact, if you calculate for example, the 8th Fibonacci number, which is 21, you can substitute into this equation when lambda 1 is raised to the power 8, and you will come up with the number 21 exactly. Okay. So try to summarize the solution of difference equations using eigenvalues and eigenvectors. Okay, so the most important thing is calculation of a to the k, because in difference equations the process is repeated, okay, for every k. Now uk plus 1 equals a times uk. The solution is uk is equal to a to the power k times u0. Now the eigenvector matrix S produces A equal to S lambda S inverse. This is a factorization of the matrix A, like A equals LU, or A equal to Q times R, as we have seen before. The new factorization is suitable for computing powers of A. So for example, A square is S lambda S minus 1 times S lambda S minus 1, but S inverse S equals the identity matrix I, so this becomes lambda squared. So S lambda square S inverse. So if you raise it to the power k, again it is S lambda to the k S inverse. So the eigenvector matrix of A to the k is still S, and the eigenvalue matrix is lambda to the power k. When A is diagonalized, A to the k U0 is easy to compute. So if we summarize the steps, we start with finding the eigenvalues of A and n independent eigenvectors. Okay, and then we write U0 as a combination of the eigenvectors U0 C1 x1 plus T2 x2 plus Cn xn. Okay, and then we multiply each eigenvector by lambda I to the k to find uk. So it is C1 lambda 1 to the k x1 plus plus Cn lambda n to the k xn. So to find the Ci's, we solve U0 equal to SC. Okay, or C equal to S inverse U0. The solution becomes UK equals A to the k U0, which is S lambda to the k times C. Okay. Example 3. Compute a to the k when s and lambda and s inverse contain whole numbers. For example, this is A, 1, 1, 0, 2. This is a triangular matrix, an upper triangular matrix, so the eigenvalues are the pivots. Lambda 1 equals 1, lambda 2 equals 2. So x1 is 1, 0, and x2 will be 1, 1. Okay, and then we can calculate a to the power k, okay, using s and s inverse. We calculate s inverse, okay, and the diagonal matrix is lambda to the k, 1 to the k, 2 to the k. So a to the k will be 1, 2 to the k minus 1, 0, 2 to the k. So with k equals 1, we get a. With k equals 0, we get I. And with k equals minus 1, we get A inverse. Okay, the zeroth power of every matrix is I equal A to the 0, and we do not know A to the 0 if A is singular. So A has to be non-singular for this case.